Hello there, and welcome to the Sleepy Space Channel. There is one place in the universe that is colder than space itself. Out around a dying star, a soft cloud of gas has chilled to within a single degree of the coldest temperature that can possibly exist. Colder than the empty dark between the galaxies, colder than the faint glow left over from the beginning of everything. It should not be possible, and yet it has been measured, and it is real. Tonight, we follow the cold all the way down, from the chill of empty space to that one quiet place that beats it, to the strange chambers where the coldest matter of all has been found, and at last toward a floor that nothing in the universe is ever allowed to reach. If you find these quiet explorations worth your time, a like or a subscribe helps the channel reach others who do. Thank you for being here. But for the next couple of hours, none of this is anything you need to carry. There is nothing here to fear, and nothing you must hold on to. Settle in, and let yourself grow still. Let your shoulders soften. Let your breathing slow. Let the day fade gently away. Let's begin. Cold is one of the few things that feels like a presence, even though it is really an absence. On a winter night, it seems to press in from outside, to seep through the windows and gather in the corners of a room. It feels like something arriving. But cold is not a thing that travels, and it is not a force that pushes. Cold is what is left when warmth drains away, and to understand how cold the universe can become, it helps to begin with that quiet, slightly unsettling fact. Everything around you is in motion, even the things that look perfectly still. The atoms that make up this page, the air, your own hands, are never at rest. They tremble and jostle and drift against one another in a constant, invisible stir. That motion is what we feel as warmth. When the atoms move quickly, an object is hot. When they slow down, it grows cold. Temperature, in the end, is only a measure of how vigorously the smallest pieces of matter are shaking. This is why a cup of tea cools on a table and never warms back up on its own. The fast motion inside the hot liquid gradually passes to the slower air around it, spreading out until everything shares the same gentle stir. Warmth always flows from the lively toward the still, never the other way, unless something works to push it. Left alone, the universe trends toward sameness, toward an even and unhurried calm. So when we ask how cold something can be, we are really asking how slow its motion can become. The colder a thing is, the more its inner trembling has quieted. And that gives the whole question a shape, because slowing has a limit in a way that speeding up does not. There is no fastest possible motion that sets a ceiling on heat. You can always pour in more energy and make a thing hotter. But there is a slowest possible state, a point past which motion cannot decrease because there is simply nothing left to take away. That point is the floor of all temperature, and almost everything in this long night is a slow descent toward it. We will travel from the ordinary chill of empty space, which is colder than most people imagine, down past a single quiet place that has somehow grown colder than space itself, and further still into chambers built by human hands, where matter rests nearer to perfect stillness than anywhere in nature. And at the very bottom, we will find a floor that can be approached forever and never quite reached. It is worth saying plainly, here at the start, that none of this is meant to alarm. The cold of the universe is not a hostile thing waiting in the dark. It is the natural condition of almost everything, the resting state that matter settles into when it is left undisturbed. The warmth we know, the warmth of stars and fires and living bodies, is the exception, gathered into small, bright points, scattered through an enormous and patient quiet. Think of warmth as activity, and cold as rest, and the universe begins to look less like a frozen waste and more like something mostly asleep. The stars are the few places still awake, still burning, still stirring their surroundings. Everywhere else, the trembling has slowed almost to nothing, and the temperature has fallen to within a few small degrees of the lowest it can go. To measure these small degrees, scientists use a scale built for exactly this purpose. It does not begin at the freezing of water, the way the everyday scales do, with their comfortable zero set at the edge of an ordinary winter. It begins instead at the very bottom, at the coldest temperature that can exist, and counts upward from there. On that scale, the freezing of water is not zero at all, but a number well up the ladder, and room temperature is higher still. The bottom of the scale, the place where motion would finally cease, sits a long way below the cold of any winter Earth has ever known. That bottom has a name and a precise value and a strange and beautiful set of rules that govern how close anything can come to it. Before we travel out into the cold places of the sky, it is worth pausing there, at the foot of the scale, to understand what absolute zero really is, and why it behaves less like a number and more like a horizon. It is a strange habit of the mind to feel cold as something that comes toward us. We say the cold crept in, the cold bit at our fingers, the cold found its way through the door, as though it were a creature with intentions, moving through the world looking for warmth to take. But the warmth was always the active thing, leaving on its own, flowing away toward the stillness around it. What we feel as cold arriving is really warmth departing, and the difference matters more than it might seem, because it tells us that cold has no engine of its own. It does not need to do anything. It is simply what is there when warmth has gone. For most of human history, no one knew there was a bottom to the cold at all. People knew that water froze, that winters could be bitter, that high mountains held snow through the summer, but the idea that cold might run out, that there could be a coldest possible temperature, came only slowly. It arrived hand in hand with the understanding that warmth is motion. Once that single idea took hold, that to be warm is to be in motion, and to cool is to slow down, the existence of a flaw followed as surely as night follows the setting of the sun. A thing can slow until it stops, and it cannot slow past stopping. The amount of motion hidden inside ordinary matter is hard to picture because it is so completely invisible. In the air of the room around you, countless atoms are flying about at speeds faster than sound, colliding billions of times each second, in a ceaseless and furious stir that you feel only as gentle warmth. All of that frantic activity is what room temperature actually is. To cool the air would be to slow that storm, to quiet the collisions, to bring the racing atoms gradually toward calm. And the cold of space, and the colder cold of the dying star, and the colder cold still of the laboratory, are simply that storm slowed further and further toward a stillness it can approach but never fully reach. There is a gentleness in understanding cold this way, as warmth leaving rather than cold arriving. It means the cold is never chasing us, never hunting, never reaching out with any will of its own. It is only the quiet that remains when the warmth has drifted off to even itself out among everything around. The whole long descent we are about to make, from the chill of space to the lowest cold ever reached, is really a descent into greater and greater quiet, into stillness, gathering wherever the warmth has had time to leave. And there is nothing in that to fear, only something to grow calm beside. For now, it is enough to carry one simple idea forward into the dark. Cold is not something that comes for us. It is what remains when motion grows quiet, and the universe, almost everywhere, is very quiet indeed. The question of how cold it can get is really the question of how completely a thing can come to rest. And the answer, as we will slowly find, is almost completely, but never quite, never entirely, never all the way down. Absolute zero is the name we give to the bottom of the temperature scale, the coldest that anything can possibly be. It sits at about minus 273 degrees on the Celsius scale, or about minus 460 degrees on the Fahrenheit scale, far below the cold of any blizzard, any polar night, any frozen ocean. On the scale physicists use for this kind of work, it is simply zero, the number from which all other temperatures are counted upward. What makes this temperature special is not just that it is very low. It is that it marks an end. As an object cools, the motion of its atoms slows, and at absolute zero that motion would slow as far as it possibly can. There would be nothing left to remove, no more warmth to take away, no slower state to fall into. It is the natural floor of all temperature, the place where the long descent finally runs out of room. For a long time, before this was understood, people imagined that cold might go on without limit, the way heat seems to. If you can always make a fire hotter, the reasoning went, perhaps you can always make ice colder without any stopping point. But the discovery that temperature is really motion changed that picture entirely. Once you know that cooling means slowing, the existence of a bottom follows naturally. A thing can only slow until it has stopped, and it cannot slow any further than stopped. The floor was there all along, waiting to be named. The scale that begins at this floor is a gift to anyone who studies the cold, because it lets the smallest temperatures be spoken of clearly. On the everyday scales, the profound cold becomes a clutter of large negative numbers, awkward and hard to picture. On the scale that starts at the bottom, the cold of empty space is a little under 3. The coldest natural place we know is around 1, and the coldest laboratories reach numbers so close to 0 that they must be written as fractions with many zeros after the point. The scale turns the abyss of cold into a clean and gentle ladder, counted upward from the quietest possible state. It helps to place a few familiar things on that ladder, to feel where we live. A comfortable room sits a few hundred steps up from the bottom. The freezing of water is a little lower, but still well up the scale, a couple of hundred steps above absolute zero. The coldest natural places on the surface of the Earth, the high plateaus of the polar winter, barely move the needle. They are still hundreds of steps above the true floor. Everything in our ordinary lives, even the things we call freezing, happens near the warm top of the ladder. The real cold begins far below, out where the air itself would turn to liquid and then to solid, and keeps going down from there. And here is the first hint of the strangeness that waits at the bottom. Absolute zero is not just another rung on the ladder, one more step you could take if you had a good enough machine. It behaves like a limit that recedes as you approach it. The closer a thing comes to the bottom, the harder it becomes to go any lower, and the smaller each further step becomes. The floor is real, and it is fixed, and yet nothing has ever touched it, and the rules of nature seem arranged so that nothing ever will. This gives absolute zero a quality more like a horizon than a destination. A horizon is a real line. You can see it clearly, you can walk toward it for as long as you like, and you will never reach it because it is defined by your distance from it. Absolute zero is something like that for temperature. It is a genuine boundary, the true bottom of the scale, and at the same time it is a place no object can actually arrive at, only draw nearer and nearer to without end. We will return to why this is so, near the close of the night, because the reasons reach into the strangest and gentlest corners of physics. For now it is enough to hold the shape of the answer in mind. When we ask how cold the universe can get, the bottom of the scale is the target, the floor everything falls toward. But the honest answer is not that the universe reaches the floor. It is that the universe comes astonishingly close, closer than the mind can easily picture, and stops just short, always just short, by the smallest possible margin. There is something quietly reassuring in that, once it settles. It means that perfect stillness, total and final, is not something nature actually permits. Even the coldest thing that could ever be keeps a trace of motion, a last faint tremor that cannot be taken away. The universe does not allow anything to stop completely, not the warmest star, and not the coldest cloud, and we will see by the end why that last small motion is built into the very fabric of things. But to feel how remarkable that is, we first need to leave the comfortable top of the ladder behind and travel out to where the real cold begins. The nearest example is closer than you might think, all around the Earth, just past the thin shell of warm air we live inside. It is the cold of space itself, and although it is not the coldest cold there is, it is colder and stranger than most people ever realize. It helps to sit for a moment with what it would actually mean for motion to stop. In every solid, the atoms are locked into place but still vibrate, trembling around their fixed positions like a held note. In every liquid and gas, they move more freely, sliding and flying and colliding. To cool any of these is to calm that trembling and that flying, to bring the atoms closer and closer to rest. Absolute zero is the imagined end of that calming, the point where even the smallest vibration would cease, where the held note would finally fall silent. It is the stillness at the very bottom of all matter. The scale that counts upward from this bottom was a quiet triumph of careful thought, because it required imagining the coldest possible state before anyone could come anywhere near it. No one had ever made something that cold, and no one knew yet whether it could be reached. But by studying how gases behaved as they cooled, by noticing how they shrank in a steady and predictable way as the temperature dropped, it became possible to trace that shrinking forward to the point where, in principle, it would run out, and to name the temperature where it did. The bottom of the scale was found by reasoning toward it from above, long before any hand came close to touching it. What makes absolute zero feel less like a number and more like a wall is that nature seems to guard it. The closer anything is brought to the bottom, the more fiercely the last scraps of warmth cling on, and the harder it becomes to remove them. It is as though the universe has built a kind of patience into the descent, slowing every approach, ensuring that the final stretch takes forever. We will see, near the end of the night, that this guarding is not an accident, but a consequence of the gentlest and strangest rules in all of physics, the rules that govern the very smallest things. It is worth noticing, too, that the bottom of the scale is the same everywhere, for everything. There is one absolute zero, and it is the same for a cloud of gas around a dying star, for a wisp of atoms in a laboratory, and for the whole universe as it cools across the ages. Every cold thing in all of creation is falling toward the very same floor, the single lowest temperature there can be. The cold is not many different bottoms, but one shared bottom, approached from every direction by everything that cools, and reached, in the end, by nothing at all. It is a strange and humbling thought that the bottom of the temperature scale was understood before it was ever approached. Long before any laboratory came near it, the existence of an absolute zero was already certain, traced out by reasoning alone, a destination named on the map before any traveler had gone there. That is part of what makes it feel so solid, so unarguable. It is not a place we stumbled upon and then measured. It is a limit we knew must exist from the very nature of warmth and motion, a floor whose reality was settled long before the first true cold was ever made. So let us climb down from the warm rungs where freezing and blizzards live, and step out into the dark between the worlds, where the temperature falls to within a few small degrees of the bottom, and where, against all expectation, even that is not the end of the descent. If you could leave the Earth behind and drift out into the space between the planets, far from the sun, your sense of cold would have to be remade. The space between worlds is not merely chilly. It is colder than anywhere on Earth by a margin almost beyond comparison, and yet, surprisingly, it is not as cold as it could be. The space between the stars and the galaxies holds a faint, steady warmth, a temperature that has a precise value and a quiet and ancient origin. That temperature is a little under 3 degrees above the bottom of the scale, around 2 7/10 on the cold counting ladder, which works out to roughly minus 270 degrees on the everyday scale. This is the ambient temperature of the universe at large, the temperature that any object far from a star will slowly settle toward if it is left alone. Drift far enough from every source of warmth, wait long enough, and this is the cold you would come to share. What is strange is that empty space has any temperature at all. Emptiness, you might think, should have no warmth to measure, nothing to be hot or cold. But space is never perfectly empty. It is filled, everywhere and in every direction, by a faint sea of light left over from the beginning of the universe. This light is the oldest thing there is, released when the young cosmos first cooled enough to become clear, and it has been traveling ever since, stretched and softened over an enormous span of time until it has cooled to that gentle value, a little under 3 degrees above the floor. This leftover glow is the reason empty space is cold, but not absolutely cold. An object floating in the dark is bathed on all sides by this ancient light, and that light carries a small amount of warmth. No matter how the object tries to cool, it cannot fall below the temperature of the light surrounding it, because that light keeps gently pouring its faint warmth back in. The glow sets a floor beneath ordinary cooling, a soft blanket of warmth that fills the whole sky and holds the temperature of empty space a few small degrees above the true bottom. It is worth letting the strangeness of that settle. The coldest natural blanket in the universe, the thing that warms even the emptiest gulfs between the galaxies, is the faded light of the universe's own birth. Everywhere you could possibly go, in any direction, that light is there. The same to remarkable precision, a uniform whisper of warmth filling all of space. It is the closest thing the cosmos has to a single shared temperature, and it is very, very cold. This background warmth is also astonishingly even. Measured across the whole sky, in every direction, it holds nearly the same value, varying only by the tiniest fractions from place to place. The universe, at its largest scale, is one of the most uniform cold things imaginable, a smooth and gentle field of faint light at a single low temperature wrapped around everything. The stars and galaxies are small, bright disturbances scattered through this calm, and the calm itself is cold and steady and old beyond reckoning. For a long time, it was reasonable to think of this background as the coldest a natural thing could be. After all, it reaches everywhere. It falls on every cloud and every world. Nothing seems able to hide from it. If the whole universe is bathed in a faint warmth a few degrees above the bottom, then surely nothing could be colder than that gentle floor, because the glow would always be there to warm anything colder back up to its own temperature. That reasoning is sensible, and for almost everything in the universe it is true. The clouds of gas between the stars, the drifting dust, the dark and empty gulfs all settle toward that background temperature and rest there. The leftover glow is the great equalizer, the warmth that nothing can sink beneath, the lowest natural temperature, the universe seems to allow. And yet there is one known place that breaks the rule. Somewhere out among the stars, in a single quiet cloud around a dying sun, the temperature has fallen below the background glow itself. There is a place that is colder than the leftover light of the beginning, colder than the blanket that warms all of space, colder, in plain terms, than space itself. It should not be possible, and yet it is real, and it has been measured, and the story of how it came to be is one of the gentlest and most surprising in all of astronomy. To understand it, we have to set aside the idea that the background glow is an unbreakable flaw. It is a flaw only for things that have no other way to cool. Give a cloud of gas a way to shed its warmth faster than the glow can pour warmth back in, and it can, for a while, slip below the background temperature. The universe has found exactly such a way, in the death throes of a certain kind of star, and the result is the coldest natural place anyone has ever found. The evenness of the background glow is one of the most remarkable facts about the universe, and it is worth dwelling on. If you could measure the temperature of the empty sky in one direction, and then turn and measure it in the exact opposite direction, across the whole width of everything, you would find the two values agree to within tiny fractions of a degree. The universe, at its largest scale, is smoother and more uniform than almost anything we ever encounter at human size. The cold that fills it is not patchy or uneven. It is a single, gentle, all-pervading calm, the same in every direction we can look. This uniform cold is also a kind of memory. The glow that fills the sky carries within it the imprint of the universe, as it was when that light was first set free, an enormous span of time ago, when the whole cosmos was young and warm and newly clear. Every faint variation in the background, every tiny place where it is a hair warmer or cooler than the average, is a trace of the conditions in that distant beginning. The cold of empty space is not a blank. It is the faded, stretched, and cooled record of the universe's earliest light, holding its first patterns still, written across the whole sky in temperatures a few degrees above the bottom. And because this glow reaches everywhere and warms everything, it acts as the great equalizer of the cosmos. Any object, left alone, given enough time, will exchange warmth with this background until it shares its temperature, neither warmer nor cooler. The glow is the resting point that everything drifts toward, the common temperature the universe gently enforces. This is exactly why the one place colder than the glow is so startling, for it means something there has found a way to resist the equalizing, to hold itself below the temperature that everything else is pulled toward, at least for a little while. It is a quiet thing to carry, that the emptiest reaches of the universe are not truly empty, and not truly without warmth. Even in the gulfs between the galaxies, where there is almost nothing at all, the old light of the beginning is still there, still faintly warm, still holding the temperature a few small degrees above the bottom. There is no corner of space so remote that this gentle glow does not reach it. The whole universe is wrapped, everywhere, in the same soft and ancient light, and that light is the warmest thing that most of the cosmos will ever know. So we leave the even ancient warmth of the background behind, that faint sea of old light that fills the whole sky, and we travel toward the one place known to have grown colder than it. It is the cloud around a dying star, and it is colder than space itself, and how it got that way is where this long night truly begins to open. Some thousands of light years from here, around a star in the slow act of dying, there is a cloud of gas that holds the lowest natural temperature anyone has ever measured. Its temperature is about 1 degree above the bottom of the scale, which is to say roughly -272 on the everyday scale. That is colder than the background glow of the universe. It is colder than the leftover light of the beginning that warms everything else. It is, as far as anyone knows, the only natural place that has chilled itself below the temperature of space itself. To feel how strange this is, hold the picture of the background glow in mind, that faint warmth filling every direction, falling on everything. It falls on this cloud too. By every ordinary expectation, the cloud should be warmed by it, like any other cold and distant thing, up to a little under 3 degrees above the bottom and no lower. Instead, it sits at about 1. Something is pulling the warmth out of it faster than the background can put warmth back in, holding it for a brief stretch of its history below the temperature of the whole rest of the sky. This cloud is the shell of gas thrown off by a star near the end of its life. Stars like our sun do not end in a single bright catastrophe. They end slowly, swelling and shedding their outer layers in great soft expulsions, casting off their own substance into the surrounding dark. What is left behind glows for a time as a beautiful expanding cloud. This particular cloud was caught in an unusually early and unusually violent moment of that long ending, and in that moment it became the coldest thing in the known natural universe. The way astronomers found its cold is one of the quietest and most elegant stories in the study of the sky. Normally we discover things in space because they shine. We look for light and trace it back to its source. But this cloud is colder than the background light behind it, and a cold thing set against a warmer glow does not add to that glow. It absorbs a little of it. So the cloud revealed itself not as a brightness, but as a shadow, a faint patch of extra darkness against the universe's own gentle light. The coldest place we know announced its presence by dimming the oldest light there is. It is a small reversal of everything we expect, and a beautiful one. Almost every object ever found in the sky was found because it gave off light. This one was found because it took a little light away. It is a hole in the warmth, a cool shadow cast on the glow of the beginning, and within that shadow lies the lowest temperature nature has ever been seen to reach. The cold of this cloud is not spread evenly through it, and it does not last. The lowest temperatures are found in a particular expanding region, a fast-moving shell racing outward from the dying star. There, in that rushing gas, the temperature has dropped to about 1 degree above the bottom. Closer in, and later in time, the gas is warmer. The profound chill belongs to a specific place and a specific moment in the cloud's unfolding. We are seeing it during a brief window, a passing phase in a process that will eventually let the gas warm back to the ordinary temperature of space. That impermanence is part of its quiet poetry. The coldest natural place in the universe is not a permanent fixture, not a fixed landmark that has always been cold and always will be. It is a moment, a phase, a thing happening, the way frost on a window is a thing happening rather than a thing that simply is. In time, the cloud will thin and spread, the rushing gas will slow, and the temperature will rise gently back toward the background glow, and the title of coldest place will pass, perhaps, to some other dying star elsewhere, in some other quiet act of ending. What does it feel like to imagine such a place? It is enormous, far larger than the distance between our sun and its neighbors, a soft and expanding cloud lit faintly by the fading star at its center. It is silent, as all of space is silent. And it is colder than the dark around it, a region where the gentle warmth that fills the rest of the universe has, for a little while, been undone. If you could rest somewhere in that cloud, you would be in the coldest, natural place that anyone has ever found, colder than the sky, colder than the old light of the beginning, held in a stillness that the rest of the universe does not quite reach. And the question that follows naturally is how? How can a cloud of gas, bathed in the same warmth as everything else, grow colder than its surroundings? What could possibly pull heat out of it faster than the oldest light in the universe pours heat back in? The answer turns out to be something familiar, something you have felt yourself on an ordinary day, made enormous and turned loose in the death of a star. It is the simple everyday physics of a gas that expands. When gas spreads out quickly into a larger space, it cools, and if it spreads out quickly enough and freely enough, it can cool a very great deal. The dying star at the center of this cloud is throwing its gas outward at tremendous speed, letting it expand into the surrounding emptiness, and that runaway expansion is the engine of the cold. It is the same effect that chills the air rushing from a can, the same effect that makes your breath feel cool when you blow it out hard, scaled up to the size of a dying star and aimed into the dark. It is worth lingering on just how thin the margin is, and yet how meaningful. The background glow rests a little under 3 degrees above the bottom of the scale, and the coldest part of the dying star's cloud rests at about 1. The difference is less than 2 degrees, a gap that would mean nothing in the warmth of ordinary life, where temperatures swing by tens of degrees between morning and afternoon. But down near the bottom of the scale, where everything is already so close to stillness, those 2 degrees are an enormous distance, the difference between resting at the temperature of all of space and slipping below it into a cold that nothing else in nature shares. Picture the cloud as it would appear if you could somehow stand back and see it whole. At its center is the fading star, no longer the steady sun it once was, swollen and dimmed and shedding its outer self into the dark. Around it spreads the cloud, soft and enormous, lit faintly from within by the dying star's last light. And within that cloud, in the fast-moving gas racing outward, lies the coldest natural place anyone has ever found, a region of stillness, colder than the sky, held for a brief moment in the long unfolding of a star's end. It is beautiful, in the quiet way that fading things often are. There is also a lesson hidden in how the cloud was found, in that it dimmed the oldest light rather than adding to it. It reminds us that the universe is not only made of the things that shine. There are cold things, quiet things, things that announce themselves only by the faint shadow they cast against a brighter background. The coldest place we know is one of these, a patch of extra dark against the gentle glow of the beginning, found not by its brilliance, but by its stillness, not by what it gives off, but by the little it quietly takes in. What lingers, after the strangeness fades, is the tenderness of it. The coldest natural place we know is a star in the act of dying, and the cold it makes is not harsh but still, not a violence but a quieting. The fading sun at its center casts its last soft light across a cloud, colder than the sky, a cloud that will, in time, warm and thin and disperse, the cold passing as gently as it came. It is the kind of cold that asks nothing and threatens nothing, only rests there in the dark, the quietest place in all of nature, for as long as its brief moment lasts. So, to understand the coldest place in the universe, we have to understand the gentlest of mechanisms, the cooling that comes from letting a gas expand. It is a thing you can feel on your own hand, and it is the reason a cloud around a dying star has become colder than space itself. That is where we turn next, into the quiet machinery of expansion and the strange refrigerator that a dying star built without ever meaning to. There is a small experiment you can do with nothing but your own breath. Hold your hand a little distance from your mouth and breathe out slowly, with your lips relaxed and open wide, and the air feels warm. Then purse your lips into a narrow gap and blow, and the very same breath from the very same body, feels cool against your skin. Nothing about the warmth inside you has changed. What changed is that the air, forced through a narrow gap, rushed out and expanded quickly into the open, and expanding gas cools. You have felt, in that small moment, the exact principle that makes the coldest place in the universe. The rule behind it is simple to state. When a gas expands into a larger volume, especially when it does so quickly and against little resistance, its temperature falls. The reason fits with everything we have said about cold being slowed motion. As the gas spreads out, its energy of motion is spread across more room, and, in pushing its way outward, the gas spends some of that energy, and what remains is a slower, cooler stir. Let a gas expand fast enough and far enough, and you can chill it dramatically. This is not an exotic effect. It is the principle behind nearly every refrigerator and air conditioner ever built. Inside those machines, a gas is compressed and then allowed to expand, and in expanding, it cools, and that coolness is carried where it is wanted. The cold air that spills out when you open a freezer is, at its root, the same physics as your cooled breath, the same physics as a can of compressed air growing frosty as it empties. Expansion is one of the most reliable ways to make something cold, and nature knows the trick as well as any engineer. Now picture that same effect, not in a machine, and not in a breath, but in the dying of a star. At the center of the coldest cloud is a star near the end of its life, and it is not shedding its outer layers gently. It is casting them off in a fast and powerful outrush, flinging gas away from itself at extraordinary speed, far faster than the slow, soft winds most dying stars produce. This is one of the fastest such outflows ever measured, a brief and forceful gust of a star throwing its own substance into the surrounding dark. That gas rushes outward into the near emptiness around the star, and as it goes, it expands enormously and almost freely, with very little around to push back against it. This is expansion cooling at its most extreme, a gas spreading out as fast and as freely as nature allows. The warmth is drained out of it as it races outward, and its temperature plunges, falling below the temperature of the ordinary gas around the star, falling below even the background glow of the universe, all the way down to about 1 degree above the bottom of the scale. So the coldest place in the universe is, in the plainest terms, a refrigerator. It is the same kind of machine as the one humming in your kitchen, running on the same principle of a gas allowed to expand. The only differences are scale and intention. This refrigerator is larger than the space between stars, and no one built it. It assembled itself out of the death of a sun, and it cools not a carton of food, but a cloud of gas larger than a solar system. And it does so simply because a dying star happened to throw its gas outward fast enough and freely enough to chill it below the temperature of space. The speed is the secret. Most dying stars shed their layers slowly, in gentle winds, and gentle winds do not cool the gas very much. It expands lazily and stays close to the background temperature. This particular star is different. Its outflow is fast and forceful, an unusually violent gust in the long quiet of its ending, and that violence is exactly what drives the cold so far down. The faster the gas is flung outward, the more freely it expands, and the more freely it expands, the colder it becomes. The coldness is a direct fingerprint of the speed. There is a strange gentleness hidden in that. The most peaceful temperature in the known universe, the lowest and stillest natural cold there is, was produced by one of the more forceful events a quiet star can undergo. A star tearing off its own outer layers, flinging them into the dark at great speed, accidentally created the calmest cold place anyone has ever found. The violence and the stillness are the same event, seen from two sides. The throwing away is what made the rest. And like the cold itself, the engine does not run forever. The fast outrush will slow as it pushes farther from the star and meets more of the surrounding gas. The expansion will become less free, the cooling will weaken, and the gas will begin its long warming back toward the temperature of space. The refrigerator built by the dying star runs only for a geological instant, a brief window in the slow unfolding of the star's death, and we happen to be watching during that window while the cold is still at its lowest. It is humbling, in a quiet way, to realize that the coldest place we know is not a careful achievement, but an accident of physics, the same accident that chills your breath and frosts a can of air, written across the death of a star. There is no special substance there, no exotic new kind of cold, only ordinary gas expanding very fast into the dark and cooling as any gas would. The universe made the coldest natural place out of the most everyday of effects, simply by letting it run at the scale of a dying sun. The cooling power of expansion is so reliable that it shapes a great deal of the everyday world without ever being noticed. The cool air that pours from a vent on a warm day, the frost that gathers on a valve as gas rushes out of a tank, the chill of a spray can held down too long, all of these are the same effect, gas expanding and cooling as it spreads into more room. It is one of the most dependable tricks in all of physics, and it asks for nothing exotic. It needs only a gas, and room for that gas to expand into, and some speed in the expanding. What sets the dying star apart is that it has all three of these in the extreme. It has an enormous quantity of gas, the whole outer envelope of a star. It has almost limitless room to expand into, the near emptiness of space around it. And it has remarkable speed, an outflow racing away far faster than the gentle winds of most dying stars. With so much gas expanding so freely and so fast into so much room, the cooling is carried to a depth that no ordinary process on a planet could approach, all the way below the temperature of space itself. It is worth holding the contrast in mind, because it is the quiet center of this part of the story. The very same physics that cools your breath, a thing so small and ordinary that you have done it without thought 1,000 times, is what made the coldest natural place in the known universe. There is no special or exotic mechanism out there around the dying star, no new and unfamiliar kind of cold. There is only an everyday effect, the cooling of expanding gas, allowed to run at the scale of a star and aimed outward into the dark. The universe made its coldest place out of the most familiar of materials. And there is a quiet wonder in realizing that the universe needed no special ingredient to make its coldest place, only an ordinary effect allowed to run without restraint. The same cooling that you can feel on the back of your own hand, if you blow across it through narrowed lips, is the entire secret of the coldest cloud in the sky. The universe is full of such echoed effects, the small and the enormous sharing a single physics, the familiar trick of a cooling breath written once across the death of a star and producing the stillest cold that nature has ever been seen to hold. It is worth carrying away from this the simple idea that distance and shadow are two faces of the same thing, two ways for warmth to fail to arrive. A world can be cold because the fire is far, or cold because the fire is hidden, and in either case, the result is the same gathering quiet, the same slow settling toward the temperature of the surrounding dark. The universe has many ways of letting warmth fall short, and wherever it does, the cold simply gathers, patient and undemanding, in the spaces the warmth never reached. For a long time, that cloud held the title of the coldest known place anywhere, natural or otherwise. But the descent does not end with a dying star. There is colder still to be found, and the colder places are not light years away in the dark around some distant sun. They are here, near at hand, in quiet rooms on the surface of the Earth, where patient hands have learned to cool small clouds of atoms to temperatures that nature, left to itself, has never reached. Before we travel there, though, it is worth lingering closer to home, among the cold corners of our own small corner of the sky. Before we follow the cold all the way down to the laboratories, it is worth walking through the cold places nearer to us, the ones within our own family of worlds. They make a kind of staircase, each step a little colder than the last, and they teach a simple lesson about where cold comes from. A surface grows cold for two plain reasons: because little warmth reaches it, and because whatever warmth it has can escape easily into the dark. Consider the worlds far from the sun. Out past the great giant planets, at the edge of the sun's family, there are small icy worlds where the sun is no longer a warming presence, but only a very bright star, one point of light among many. So little of its warmth reaches that distance that the surfaces there fall to around -230 on the everyday scale, only a few tens of degrees above the bottom. On such a world, what we call air on Earth would lie frozen on the ground. Warmth, in any sense we would recognize, is a memory of somewhere else. These distant worlds are cold simply because they are far. The warmth of the sun thins out with distance, spreading thinner and fainter the farther it travels, until at the edge of the sun's reach there is hardly any left to feel. A world out there receives only a faint trickle of the warmth that bathes the Earth, and so it settles into a cold that holds steady through its long, slow years. It is a cold of distance, the chill of being far from the only fire for light years in any direction. But there is a stranger and colder kind of place, much nearer than those distant worlds, and it does not require great distance at all. It requires only shadow, the right kind of shadow, held without break for an enormous span of time. On the Moon, and on the small innermost planet closest to the Sun, there are craters near the poles whose floors are tilted just so, sheltered by their own rims, such that across billions of years no sunlight has ever reached the bottom. These are the permanently shadowed places, and they are among the coldest surfaces in the entire family of the Sun. It is worth pausing on how surprising that is. On the very world closest to the Sun, scorched on its sunlit face to temperatures that would melt some metals, there are pockets of permanent shadow near the poles that rank among the coldest places anywhere near us. The same world holds, side by side, some of the hottest and some of the coldest surfaces in the Sun's family, separated only by whether sunlight has ever managed to fall there. Where the light reaches, it bakes. Where the light has never reached, the cold has gathered undisturbed since the world was young. These permanently shadowed floors act as cold traps. Because they are never warmed, anything that drifts into them and freezes can stay frozen, held in place for ages. Water and other ices that wandered there long ago have remained, locked in the cold and the dark, because nothing has ever warmed them enough to let them escape again. These shadowed craters are, in a sense, the oldest cellars in the Sun's family, holding their ancient frost since before there was life on Earth, simply because the warmth has never come to thaw them. The other reason a place grows cold is that its warmth can escape easily, and this is why airless worlds cool so sharply on their night sides. On the Earth, a blanket of air holds warmth close, carrying it around, smoothing the difference between day and night, keeping the dark side from falling too far. A world with no air has no such blanket. When its surface turns away from the sun, the warmth radiates straight off into the dark with nothing to hold it back, and the temperature plunges far faster and far further than it ever could beneath a sky of air. This is why the night side of the moon, or of any airless world, grows so bitterly cold so quickly. There is nothing to keep the warmth in. The moment the sun sets, the heat begins streaming away into the emptiness above, and the surface chills toward the cold of space. With no air to trap it and carry it, the warmth simply leaves, and the ground is left to face the dark on its own. Cold grows fastest where there is nothing to hold the warmth in place. Put these together, distance and shadow and the lack of any blanket, and you can read the cold of any surface in the sky. The far worlds are cold because the sun is faint there. The shadowed craters are cold because the sun has never touched them. The night sides of airless worlds are cold because their warmth escapes unhindered into the dark. In each case, the cold is not an active force arriving, but simply the result of warmth being scarce, or fleeting, or free to leave. And yet all of these places, cold as they are, remain warmer than empty space itself. The distant icy worlds still feel a faint trace of the sun. The shadowed craters still hold a little warmth leaking from the rock around them. Even the coldest night side is still settling toward the background temperature, not below it. These are the cold corners of our neighborhood, the lowest chills within reach of the sun, and still they sit a few degrees above the cold of the open sky, and many degrees above the dying star's frozen cloud. Among the cold corners of our neighborhood, the permanently shadowed craters deserve a second look, because they hold a kind of cold that is also a kind of time. The ice trapped in those lightless floors has rested there, untouched, since long before the first living thing appeared on Earth. It is not refreshed or renewed. It is simply held, frozen and still, in a shadow that has never lifted. To reach into one of those craters would be to reach into the past, to touch a cold that has been gathering quietly since the world was young, undisturbed by any warmth in all the ages since. There is a gentleness to the way these cold traps keep what falls into them. A wandering scrap of ice, a stray molecule of water drifting across the airless surface, will bounce and skitter under the sun's warmth until, by chance, it falls into one of these permanently shadowed floors, and there it stops, because there is no warmth to lift it out again. Over an enormous span of time, scrap by scrap, the cold floors gather their hidden stores of ice, each piece arriving by accident and staying forever, locked in place by nothing more than the absence of light. These nearby colds also teach the difference between a cold of distance and a cold of shadow. The far icy worlds are cold because the sun is faint at their great distance, a cold spread evenly across their whole surface. The shadowed craters are cold because the sun, though near, has been blocked from ever reaching them, a cold confined to particular sheltered pockets, while the sunlit ground nearby may be searing. Both are profound colds, but they arise from different absences, the one from being far from the fire, the other from being hidden from it, and together they show how many ways the universe has of letting warmth fail to arrive. Standing among these cold corners, one begins to feel how much of the universe is simply waiting in the dark, cold, and patient, and undisturbed. The far icy worlds turn slowly in their long orbits. The shadowed craters hold their ancient frost. The night sides of airless worlds cool toward the temperature of space, and all of it rests in a quiet that has lasted for ages and will last for ages more. These are not hostile places so much as sleeping ones, cold because nothing has come to stir them, still because nothing has come to wake them, holding their long rest beneath a sky full of distant and indifferent stars. So the staircase leads downward, step by step, from the cold of distant worlds to the older cold of permanent shadow, to the swift cold of an airless night, and on past all of them to the cold of empty space, and past even that to the dying star's expanding cloud. Each step is colder than the last, and each teaches the same gentle lesson, that cold is only the absence of warmth, gathering wherever warmth is faint or free to flee. But the cold places near home are not only empty and frozen. Some of the coldest natural pockets in the whole galaxy are also the most fertile, the places where new stars are quietly being born, and that is where we turn next. Scattered through the galaxy, between the stars, drift enormous clouds of gas and dust, and the darkest and densest of them are very cold, only about 10 to 20 degrees above the bottom of the scale. They are colder than most of the space around them, shielded from the light of the stars by their own thick dust, and within that shielded cold, something quietly remarkable happens. These cold clouds are where new stars are born. The coldest pockets of the galaxy are also its nurseries. It seems at first like a contradiction. We tend to think of stars as creatures of heat, of fire and fusion and blazing light, and so we might expect them to be born in warmth. But the truth runs the other way. A star can only begin to form in gas that is cold and still and quiet. Warmth is the enemy of star formation, and cold is its necessary condition. The fire of a star is lit, at the very start, in the coldest and darkest gas the galaxy holds. The reason is gentle and worth following slowly. For a cloud of gas to become a star, it must collapse, drawing together under its own gravity until its center grows dense and warm enough to ignite. But warm gas resists collapsing. Warmth makes the atoms move quickly, and quick-moving gas pushes outward, puffing itself up, holding itself apart against gravity's slow pull. A warm cloud stays spread out, unable to gather. Only when a cloud is cold, only when its gas has slowed and stilled, can gravity finally draw it inward and begin the long collapse that ends in a star. So cold is not the absence of creation here. It is the doorway to it. In the cold clouds, where the gas has quieted and grown still, gravity can at last take hold. The cloud begins to draw together, slowly at first and then faster, gathering itself toward a center, until far inside, the gathering gas grows dense and warm and finally bright. The cold makes the stillness. The stillness lets gravity work, and gravity, in time, lights the fire. Every star that shines began in such a cold and quiet place. There is a lovely symmetry hidden in this when you set it beside the dying star and its frozen cloud. The coldest natural place we know is a star ending, throwing off its gas in a chill that runs colder than space. And the cold clouds of the galaxy are stars beginning, gathering themselves in a chill that lets gravity start its work. The same condition, profound cold, sits at both ends of a star's life, at the quiet death and at the quiet birth. Cold is where stars come from, and cold, in a different form, is where some of them go. As we have wandered through on an earlier night, the space between the stars runs cold for reasons of its own, and these clouds are colder still than the ordinary gulfs around them. Their dust acts as a shield, blocking the light of nearby stars from reaching the gas within, so that the inside of the cloud is darker and colder than its surroundings. In that shielded dark, the gas can cool further and settle further into stillness, sinking toward those 10 or 20 degrees above the bottom, cold enough at last for the slow work of gathering to begin. These clouds are also where the raw material of new worlds is kept. The same cold gas and dust that gathers into a star also gathers, in the leftover ring around it, into planets. The carbon and oxygen and iron that make up worlds and, in time, living things, drift first through these cold clouds, chilled and dark, waiting. Everything solid you have ever touched began as cold dust in such a place, gathered out of the chill and the dark into something warm and bright and, eventually, alive. The cold clouds are not only nurseries for stars, but storehouses for everything that stars will one day make. It changes the feeling of the cold to know this. The cold of these clouds is not a barren or hostile thing. It is a fertile cold, a generative cold, the necessary stillness out of which light and warmth and worlds eventually come. The galaxy makes its stars in the cold the way bread is made in the quiet dark of rising, slowly and out of sight, in conditions that look like nothing happening at all. The coldest, darkest, stillest gas is exactly where the next generation of suns is being gently assembled. And the cold of these clouds, though far below the cold of any winter, is still gentler than the cold of the dying star's frozen shell. The clouds rest at 10 or 20 degrees above the bottom. The dying star's outflow reaches down to about 1. So even among the cold places of the galaxy, there is a hierarchy. The nurseries, cold, but not the coldest. The dying star, colder still. The natural universe holds its lowest temperature in that single expanding cloud around a dying sun, and nowhere natural has been found to go lower. Nowhere natural, that is. For the lowest cold of all is not found in the sky at all, not in the dying star, and not in the star-forming clouds, and not in the empty gulfs between the galaxies. The lowest cold yet reached anywhere in the known universe was made by human hands, in quiet rooms on the surface of the Earth, where patient and ingenious work has cooled small clouds of atoms to temperatures that nature, in all its enormous reach, has never once produced on its own. It is worth picturing, slowly, how a star actually gathers itself out of one of these cold clouds, because the process is among the gentlest in all of nature. It begins with the faintest unevenness, a place in the cloud where the cold gas is just slightly denser than its surroundings. That denser place pulls a little harder on the gas around it, drawing more in, growing denser still, pulling harder yet. Over a very long span of time, this slow gathering builds, the cold gas drifting inward, grain by grain, until a center forms that is dense enough and, at last, warm enough, at its core, to begin to shine. A star is the end of a long, cold, patient falling together. The dust that shields these clouds and keeps them cold is itself a remarkable thing, for it is made of the ashes of earlier stars. The carbon and silicon and iron in those tiny grains were forged inside suns that lived and died before our own, scattered into space at their endings, and gathered again into the cold clouds where new stars now form. So the cold nurseries are built from the remains of the past, the leftovers of old stars, providing the very shielding that lets new stars be born. The galaxy makes its future, quietly, out of its own ashes, in the cold and the dark. And the cold of these clouds, for all that it enables, remains a soft and unhurried cold, nothing like a violence. Nothing is forced in a star-forming cloud. The gathering happens over spans of time so long that, to any single moment of watching, the cloud would seem to be doing nothing at all, simply resting in the cold and the dark. The making of a star is one of the slowest and most patient things the universe does, a falling together so gradual that it looks, from any close vantage, exactly like stillness. The cold and the quiet are not the absence of creation. They are its disguise. There is a comfort in knowing that the cold and the dark are where the light comes from. The stars that fill the night sky, the sun that warms the day, every point of brightness we have ever seen began in a cold and lightless cloud, gathered slowly out of stillness into fire. So the cold is not opposed to warmth and light, but is, in a sense, their cradle, the patient quiet from which all the brightness of the universe is eventually born. When we look at the cold clouds of the galaxy, we are looking at the unlit beginnings of future suns, resting in the dark, waiting their turn to shine. To follow the cold to its lowest reaches, then we must come back from the stars and return home, to a laboratory bench, to a small chamber holding a faint cloud of atoms, chilled by light and patience, to within a breath of the bottom of the scale. It is there, and not in the sky, that the coldest known place in the universe is most likely to be found. Here is a fact that gently overturns the whole picture we have been building. The coldest place in the known universe is, most likely, not anywhere in the sky. It is on the Earth, in a laboratory, and sometimes in a small chamber circling the Earth aboard the space station. In certain quiet rooms, physicists have cooled tiny clouds of atoms to within a hair of the bottom of the scale, colder than the dying star, colder than empty space, colder than anything nature has ever been found to make on its own. The numbers are hard to hold in the mind, so it is worth saying them carefully. The cold of empty space is a little under 3 degrees above the bottom. The dying star's frozen cloud reaches about 1 degree above the bottom. But in these laboratories, atoms have been cooled not to 1 degree above the bottom, and not to 1/10 of a degree, but to billionths of a degree above absolute zero, and in the most extreme work, to trillionths of a degree. They have come closer to the true bottom of the scale than any natural place ever measured, by an enormous margin. To make matter that cold, the warmth has to be removed almost atom by atom, and the methods for doing it are among the most ingenious and delicate things people have ever devised. The first surprise is that one of the main tools for making things cold is light. Light usually warms what it touches. Sunlight on your skin is warmth arriving. But light tuned with great care can be made to do the opposite, to slow atoms down instead of speeding them up, and slowing them down is exactly what cooling means. The trick works something like this. Imagine an atom moving toward a beam of light. If the light is tuned just so, the atom will absorb the light coming at it and, in doing so, receive a tiny push against its motion, a gentle nudge slowing it down. Surround a small cloud of atoms with such beams from every side, each one tuned to push back against any atom moving toward it, and the atoms find themselves slowed no matter which way they try to drift. It is as though they were moving through a thick and gentle resistance, a steady headwind made of light, and as they slow, they cool. This is laser cooling, and it can bring a cloud of atoms down to a tiny fraction of a degree above the bottom. But laser cooling alone does not reach the very lowest temperatures, and so a second method is layered on top of it, one borrowed from something as ordinary as a hot drink cooling on a table. A hot drink cools partly because its most energetic molecules escape from the surface as steam, carrying their extra warmth away with them and leaving the slower, cooler molecules behind. The same idea, applied to a trapped cloud of atoms, is called evaporative cooling. The trap is gently loosened so that the warmest, fastest atoms can escape over its edge, and as they leave, they carry off the heat, and the atoms that remain are colder than before. Done with great patience, letting the warmest atoms leak away again and again, evaporative cooling can take a cloud the last enormous distance down, from a fraction of a degree to billionths of a degree above the bottom. The cloud that remains is tiny, only a faint wisp of atoms held in a trap of light and magnetism. but it is colder than anything in the natural universe, a small patch of matter resting nearer to perfect stillness than the dying star, nearer than empty space, nearer than the cold clouds where stars are born. And there is one more refinement, which carries the coldest matter off the surface of the Earth entirely. On the ground, gravity is a nuisance for this kind of work. A cloud of ultra-cold atoms, released from its trap so it can cool a little further, immediately begins to fall, and it falls out of view before it can be studied for long. So a laboratory was carried up to the space station, where everything is in a constant, gentle freefall, and nothing weighs anything at all. There, a released cloud of atoms simply floats, held nowhere and falling nowhere, and it can be allowed to expand and cool far longer and far further than it ever could on the ground. In that floating laboratory, circling the Earth, atoms have been cooled to some of the lowest temperatures ever reached anywhere. So it is quite possible that the coldest single place in the entire known universe, at this very moment, is a small chamber aboard the space station, drifting overhead, holding a faint cloud of atoms colder than the dying star and colder than the empty sky. The lowest cold in all of creation, as far as we know it, may be passing silently over your head a few times a day. There is something quietly moving in that. The universe, in all its enormous reach, across billions of years and countless stars, never managed to cool anything below about 1 degree above the bottom. And then, on one small world, a particular kind of curious life learned how to coax matter down to billionths and trillionths of a degree, far past anything nature had ever done. The coldest place in the known universe is not a natural wonder at all. It is a made thing, the product of patience and care, and an almost tender precision, a stillness gathered deliberately where none had ever been before. It is worth being clear that these are tiny amounts of matter, faint wisps of a few atoms, held for fleeting moments in carefully built traps. No one has chilled a room, or a planet, or a cloud of gas the size of a star to these temperatures. The coldest places are small and brief and delicate. But within those small and brief and delicate clouds, matter comes nearer to perfect rest than anywhere else we know of. And in coming so near, it begins to do things that warmer matter never does. It is worth slowing down on the idea of light being used to cool, because it runs so against our everyday sense. We know light as a source of warmth. We step into a patch of sunlight to get warm. We feel the heat of a lamp held close. The notion that light could be used to chill something seems almost backward. But the cooling does not come from the light's warmth. It comes from the gentle, precisely aimed pushes that the light gives to moving atoms, each particle of light delivering a tiny shove against an atom's motion, slowing it by the smallest possible amount, again and again, until the atom is barely moving at all. The patience required is hard to overstate. To cool a cloud of atoms to billionths of a degree above the bottom is to remove almost every last trace of motion from it, nudge by nudge and escape by escape, in a process that must be controlled with extraordinary care. A single stray touch of warmth from the outside world, a faint leak of heat through the walls of the trap, would undo the work in an instant. So the coldest matter must be held in near perfect isolation, suspended in light and magnetism, touching nothing, while the warmth is coaxed out of it, a little at a time. The lowest cold is also the most delicately guarded. What is most quietly moving about this is the contrast in scale. The universe is unimaginably large, and across all of its reach and all of its ages, it never cooled anything below about 1 degree above the bottom. And then a small and curious form of life on a single ordinary world learned to do better gathering a faint wisp of atoms into a stillness colder than anything the whole cosmos had ever made. The coldest place in the known universe is not a grand natural wonder light years away. It is a small, careful human thing, made on a bench or drifting in a chamber overhead, gathered out of patience and precision and a kind of tenderness toward the very small. It is worth pausing on the quiet pride of it and also on the humility. A small and curious form of life, on one ordinary world, looked out at a universe that had never cooled anything below about 1 degree above the bottom, and then went quietly past it, gathering matter into a stillness colder than the whole cosmos had ever made. And yet that triumph was achieved not by force, but by gentleness, by coaxing and patience, and an almost loving care for the very small. The coldest place in the known universe was made by the most delicate of means, a stillness gathered tenderly, atom by atom, where none had ever been. It is a quiet marvel that the same patient care which cools these atoms also lets us watch the hidden rules of nature unfold at a size we can see. In the coldest clouds of atoms, the behavior of the very small, usually buried far beneath the reach of our senses, rises gently into view, slowed and stilled enough to be observed directly. The cold is not only the lowest place on the scale, but a kind of window, a way of quieting the world until the faint and usually hidden workings of matter can finally be seen plainly, resting almost motionless in their traps of light. For as matter approaches the very bottom of the scale, it does not simply sit there, cold and ordinary and still. It changes. It begins to behave in quiet, strange, almost dreamlike ways, revealing a hidden layer of nature that the warmth of ordinary life keeps hidden. The closer matter comes to stillness, the stranger and the more unified it becomes, and that is the next quiet wonder of the cold. When matter is brought near the bottom of the temperature scale, it stops behaving the way everyday things behave. The constant jostling of warmth, which fills all ordinary matter with restless motion, falls almost silent, and in that silence, a quieter layer of nature shows through. The rules that govern the smallest scales, usually drowned out by the noise of heat, become visible at a size people can see and touch. Cold is, in a sense, a way of turning down the noise until the quiet music underneath can finally be heard. One of the first strange things to appear is the vanishing of electrical resistance. In ordinary wires, electricity meets a kind of friction as it flows, losing a little energy to warmth along the way. This is why wires grow warm and why some energy is always wasted. But certain materials, cooled near the bottom of the scale, lose this resistance entirely. A current set flowing in a loop of such material will, in principle, circle on and on without fading, without loss, without end. The friction simply goes away, and the flow becomes perfect and tireless. This loss of resistance is called superconductivity, and there is something quietly astonishing about it. A flow with no friction is a kind of perpetual gentleness, a motion that never wears itself out. In the warm world, everything that moves eventually slows and stops, ground down by friction into stillness. But in the cold, certain currents are freed from that fate. They can flow forever, smoothly and silently, because the cold has removed the resistance that would otherwise bring them to rest. The cold gives a strange kind of permanence to motion, even as it stills the motion of everything else. Cold also transforms certain liquids in ways that seem to defy ordinary sense. Liquid helium, cooled far enough, becomes what is called a superfluid, a liquid with no thickness, no internal friction at all. A superfluid does things no ordinary liquid can. Set it swirling, and it will swirl on without slowing. Place it in a cup, and it will creep up the inner walls in a film too thin to see, flow over the rim, and gather in drops beneath, emptying the cup from the inside as though gravity were merely a suggestion. It can slip through cracks and pores far too fine for any ordinary liquid to pass. These behaviors look almost like the liquid is alive or enchanted, climbing walls and escaping cups of its own accord. But there is no magic in it, only the absence of friction. An ordinary liquid is held back by its own internal stickiness, its tendency to drag against itself and against its container. The cold removes that stickiness entirely, and what is left is a liquid that flows with perfect freedom, following the faintest pull without resistance, creeping wherever it can reach because nothing remains to hold it back. The cold has not given it new powers. It has only taken away what used to restrain it. And there is a third transformation, perhaps the strangest of all, which appears when a gas of atoms is cooled to the very bottom of the reachable range. At those temperatures, near billionths of a degree above the floor, the atoms can fall into a single shared state, blurring together until they behave not as a crowd of separate particles, but as one single thing. The distinct atoms lose their separateness and merge into a unified whole, a small patch of matter acting like one calm wave rather than a swarm of individuals. This is a state of matter that does not exist in the warm world at all, that appears only in the lowest cold. It is hard to picture, and perhaps it cannot be fully pictured, but the feeling of it is clear enough. Warmth keeps things separate and individual, each atom going its own way, colliding and scattering in endless private motion. Cold lets them fall into step. As the temperature drops near the bottom, the atoms stop behaving as a chaotic crowd and begin behaving as a single, coordinated, gentle whole. Where warmth made many, cold makes one. The lower the cold, the more the many become a single, quiet thing. This is the common thread running through all of it, the superconductor and the superfluid and the merged cloud of atoms. In each case, cold reveals a hidden unity. Warmth is chaos and individuality, every piece of matter jostling on its own. Cold is harmony and coordination, the pieces falling into a shared and frictionless calm. As motion drains away, matter does not simply freeze into a dead stillness. It organizes itself into something smoother, quieter, and more unified than it ever was when it was warm. There is something fitting in that, on the edge of sleep. We might fear that the profound cold is a kind of death, a grinding down into lifeless stillness. But what actually happens as matter cools toward the bottom is closer to a settling, a coming into harmony, a release of friction and chaos into a calm and coordinated whole. The cold does not break matter down. It smooths it out. It lets the restless, jostling pieces finally fall into step with one another and flow without resistance, as though the whole of it had at last relaxed. These strange and gentle behaviors are not curiosities only. They are among the reasons the cold is studied so carefully, for the frictionless flow of superconductors carries currents in some of the most sensitive instruments ever built, and the merged clouds of ultracold atoms let physicists watch the rules of the very small play out at a visible scale. The cold is a window into the hidden machinery of nature, a way of quieting the world enough to see how it truly works beneath the noise of warmth. The way a superfluid empties its own container is worth picturing slowly, because it is one of the strangest sights the cold produces. An ordinary liquid sits in its cup and stays there, held by its own weight and its stickiness against the walls. But a superfluid, freed of all friction, creeps upward along the inner surface of the cup in a film far too thin to see, climbs over the rim, and flows down the outside, gathering and dripping from the bottom, until the cup has quietly emptied itself, with no one touching it. It is not magic and not life. It is only what a liquid does when nothing remains to hold it back. The merging of atoms into a single shared state is stranger still, and it asks us to set aside our ordinary picture of matter as made of separate, countable pieces. In the warm world, the atoms of a gas are like a crowd in a square, each one a distinct individual, moving on its own path. As the gas is cooled toward the very bottom, that distinctness begins to dissolve. The atoms spread out, overlap, and blur into one another until they can no longer be told apart, and the whole cloud behaves as a single, unified thing, a patch of matter acting like one calm wave rather than a swarm of particles. Cold dissolves the boundaries between things. Taken together, these behaviors point to a single, quiet truth that is easy to miss. We tend to imagine that cold is where things break down, where matter grows brittle and dead and inert. But the profound cold reveals the opposite. As the warmth and the chaos fall away, matter does not collapse into lifelessness. It organizes. It finds a quieter order, a smoother flow, a more perfect unity than warmth ever allowed. The cold is not the end of matter's possibilities. It is the doorway to its strangest and most graceful ones, the place where the hidden order beneath the noise of warmth finally comes into view. It changes how one feels about the cold, to learn that it is where matter finds its deepest harmony, rather than its end. We might have expected the lowest temperatures to be the most lifeless, the most broken, the most inert. Instead, they are where matter flows, without friction, where separate things become one, where a hidden order rises gently into view. The cold, it turns out, is not a ruin, but a kind of homecoming, the place where the restless pieces of the world finally fall into step and rest together in a quiet they cannot find in the warmth. But the lower one goes, the harder the going becomes, and at the very bottom there waits a final and beautiful obstacle. For all the ingenuity of light and patience, for all the floating laboratories, and the careful coaxing of atoms towards stillness, the true bottom of the scale has never been reached, and never will be. Absolute zero can be approached forever and never touched, and the reason why is the quiet center of this whole long night. With laboratories reaching trillionths of a degree above the bottom of the scale, closer to absolute zero than anything in nature, it is fair to wonder why they do not simply finish the descent and reach the bottom itself. The answer is one of the most settled and most beautiful facts in all of physics. Absolute zero cannot be reached. No matter how clever the method, no matter how patient the effort, the true bottom of the scale can be approached without end and never actually arrived at. It is a floor that recedes as you draw near. Part of the reason is practical, and it grows steeper the lower you go. Every method of cooling works by carrying warmth away from a thing to somewhere colder. But the colder a sample becomes, the less warmth is left in it to remove, and the harder it becomes to find anywhere colder to carry that warmth to. Each step downward removes a smaller and smaller slice of what remains, and each step grows more difficult than the last. The descent does not stop, but it slows without limit, the way a number can be halved again and never quite reach zero. Picture walking toward a wall by always stepping halfway to it. The first step covers half the distance, the next a quarter, the next an eighth, and you draw ever nearer, but no step ever lands you against the wall, because each one only closes half of what is left. Cooling toward absolute zero is like that. Every effort brings the temperature lower, closer to the bottom, but each effort closes only part of the remaining gap, and the gap, though it shrinks toward nothing, never fully closes. The bottom is always there, always just below, always unreached. But beneath this practical difficulty lies a quieter reason, and it is the quiet center of the whole subject. Even at absolute zero itself, even at the very bottom of the scale, matter would not be perfectly still. The rules that govern the smallest scales do not permit perfect stillness. A particle resting perfectly motionless in a perfectly definite place is not something nature allows. The very smallest pieces of the world are forbidden from being entirely at rest. There is always a faint residual motion, a last small trembling that cannot be removed by any amount of cooling. This last trembling is not a flaw in our methods or a limit of our machines. It is built into the nature of matter itself. Down at the smallest scales, a particle can never be both perfectly placed and perfectly still at once. The world simply does not work that way. So even if every scrap of removable warmth were taken away, even at the theoretical bottom of the scale, a gentle, irreducible quiver would remain, a motion that belongs to existence itself and not to any warmth. It is the universe's refusal to allow anything to come completely to rest. There is something tender in that when it settles. The coldest possible state, the lowest temperature there can be, is not a perfect and final stillness, not an absolute death of all motion. Even there, even at the very bottom that nothing can reach, a small motion stays. The universe does not permit total rest. It keeps, in even the coldest possible thing, one last faint heartbeat of motion, a trembling that cannot be stilled, because stilling it would break a law more fundamental than temperature itself. So the honest answer to our question, the one we planted near the beginning, comes fully into view here. How cold can the universe actually get? It can get astonishingly cold, closer to the bottom than the mind can easily hold, to billionths and trillionths of a degree above absolute zero. But it cannot reach the bottom. It approaches the floor forever, by ever smaller steps, and stops just short every time by the smallest possible margin. The coldest thing that could ever exist still keeps its last small motion. Perfect stillness is not on offer anywhere in the universe. This is not a disappointment, though it might sound like one at first. It is, in its own way, a kind of grace. It means that absolute, final, total stillness is simply not a state the universe contains. Everything, everywhere, even the coldest cloud and the most carefully chilled wisp of atoms, keeps moving, faintly, always. The trembling never fully stops. There is no place in all of creation where motion has entirely ceased, and there never can be, because the rules of the world hold a small motion in reserve that nothing can take away. And so absolute zero remains what it was from the start, a horizon rather than a destination. It is real, and it is fixed, and it marks the true bottom of all temperature. But it is forever ahead, never beneath anyone's feet, a limit that the whole universe leans toward and never touches. The cold places we have visited, the dying star, and the empty sky, and the floating laboratory, are all on the same slow journey toward that floor, and all of them, every one, fall short of it, and always will. There is one more cold left to consider, and it is the largest of all, for it belongs not to a single cloud or a single chamber, but to the whole universe and to all of time. The cosmos itself is cooling, slowly and steadily, as the long ages pass, drifting by the same endless approach toward the same unreachable floor. The background glow that warms all of space is growing fainter and colder with the years, and the whole of creation is settling, gently, toward a cold that will spread everywhere and stay. The image of always stepping halfway to a wall is worth holding onto, because it captures the gentleness of the limit as well as its firmness. There is nothing harsh about it. No one is stopped at a barrier or turned away at a gate. The descent toward the bottom simply continues forever, each step smaller than the last, drawing ever nearer to a floor that is always just below. It is a limit made not of force, but of patience, an endless approach that never needs to end because it never quite arrives. The bottom is not defended by a wall. It is defended by infinity. The last small motion that remains even at the bottom has a quiet name in physics, and it is sometimes called the motion that cannot be removed, the trembling that belongs to existence rather than to warmth. It is there in everything, always, beneath all the warmth we could ever take away. Even in the coldest wisp of atoms in the coldest laboratory, even in the imagined perfect cold of the very bottom of the scale, this motion would remain, faint and constant and irreducible. It is the universe's way of refusing to let anything come to a perfect and final stop. And so the answer to the night's question carries within it a kind of reassurance that goes beyond physics. Total stillness, absolute and final rest, is simply not something that exists anywhere, ever. Everything keeps moving, however faintly, down to the smallest pieces of the coldest things. There is no perfect stop in all of creation, no place where motion has entirely and forever ceased. The universe holds, in everything it contains, one last small motion in reserve, and it never lets that motion go. Even the cold, even the lowest cold imaginable, is never entirely still. And so the cold keeps its last secret to the very end, which is that it can never quite finish. No matter how patient the cooling, no matter how clever the method, the bottom stays just out of reach, guarded by a trembling that nothing can remove. There is something almost kind in that refusal, as though the universe were unwilling to let anything fall into a stillness so complete that nothing remained at all. It holds back, always, one last small motion, one final faint sign of life in even the coldest possible thing, and in doing so it keeps the door open, forever, just a little. There is a kind of poetry in a limit that is enforced not by a wall, but by an endlessness, a bottom kept out of reach by an infinity of ever smaller steps. Nothing forbids the journey. The descent may continue as long as anyone likes, always lower, always nearer. It is only that the journey has no final step, no last rung where the foot comes to rest on the floor. The bottom is real, and the path toward it is open, and the two never meet. And in that gentle paradox lies the whole strange truth of how cold the universe can be. That long cooling of everything is where this night comes to rest. It is the gentlest of all the colds, the slowest and the largest, the universe itself easing towards stillness across spans of time so great that the mind can only bow before them. And like every other cold we have seen, it approaches the bottom without ever reaching it, carrying one last small motion forward, forever. There is one more cold to consider, and it is the largest of them all, for it does not belong to any single place, but to the entire universe, and to the whole sweep of time still to come. The universe is expanding, growing larger with every passing age, and as it expands, the background glow that warms all of space is stretching and cooling along with it. The faint warmth, a little under 3 degrees above the bottom, the warmth that fills the sky today, was far hotter in the distant past and will be far colder in the distant future. Run the long story forward, and the picture is one of slow and steady cooling on the grandest scale. The background glow that now rests a little under 3 degrees above the bottom will, across enormous spans of time, fall to a single degree, and then to a fraction of a degree, and then to a smaller fraction still. The whole universe, everywhere at once, will drift downward toward the bottom of the scale, growing colder and quieter and stiller as the ages pass, by the same endless approach that no cooling ever completes. The stars play their part in this long cooling, for they will not burn forever. Each star spends its fuel over its long life, and, in time, comes to its end, some gently and some less so, but all of them eventually falling dark. New stars will form for a long while yet, gathered in the cold clouds, as they always have been. But the gas to make them is finite, and across spans of time almost beyond imagining, the last stars will form, and burn, and fade. The great age of starlight, which seems so permanent to us, is a passing season in the far longer life of the cosmos. After the stars, the universe enters its long evening, lit only by the slow fading of embers, the cooling remnants left behind when stars die. These remnants will glow ever more faintly as they shed their warmth into the surrounding dark, cooling across spans of time that dwarf the whole age of the universe so far. One by one, the last lights will dim toward the temperature of the sky around them until the cosmos holds no bright points at all, only cooling cinders drifting in an ever colder dark. And then, across times longer still, even those cooling cinders will fade toward the background, and the background itself will have fallen so low that the whole universe shares a single, almost uniform, profound cold. The differences will smooth away. The hot places and the cold places will even out, the way a warm cup and a cool room eventually come to share one temperature, until the entire cosmos rests at very nearly the same faint cold everywhere, a stillness spread across all of space and held for an eternity. This is the far future the cold points toward, and it is worth meeting it gently, because it can sound bleak if it is told the wrong way. The universe drifting toward a single, even cold is not a catastrophe and not a violence. There is no fire and no collision in it, no sudden end. It is the slowest and softest of all possible endings, a long settling into quiet, the cosmos easing down toward rest, the way a day eases down toward evening, gradually, without alarm, almost imperceptibly. In a sense, the cold we found in the dying star's frozen cloud is a small early taste of this. There, in one place, the gas cooled below the temperature of the sky and rested for a while in a chill colder than space. In the far future, something like that cold will be the condition of everything, everywhere, not as a brief and passing phase, but as the settled and permanent state of the whole universe. The stillness that one dying star reached for a moment will, in the end, belong to all of creation. And yet, true to everything we have learned, even that final cold will not be absolute. The universe will approach the bottom of the scale by the same endless steps as everything else, ever closer and never arriving, always one last small motion remaining. The far future cosmos, cold and quiet and even beyond imagining, will still hold that irreducible trembling, that faint motion the rules of the world keep in reserve. Even at the end of all the ages, in the coldest the universe will ever be, there will be no perfect, final stillness. There will always be one last shiver that stays. There is a strange comfort in carrying that thought to the end. The universe is not racing toward a hard and frozen death, but easing, across spans of time we can barely name, toward a gentle and even quiet. And even in that quiet, it will never quite stop moving. The long cold ahead is not an ending so much as a settling, the great activity of stars and worlds slowly giving way to rest, the whole cosmos lying down, at last, into a stillness that is nonetheless never entirely still. It is a fitting place to let our own thoughts begin to slow. The The universe will take an unimaginable span of time to make its long descent into the cold, and we are here in its bright and early morning, in the age of stars, when warmth and light are everywhere, and the great cooling is only the faintest of distant trends. There is no need to feel the cold of that far future as a weight. It is simply the natural direction of things, the same direction a warm cup follows on a cool table, scaled up to the whole of everything and stretched across all of time. The spans of time involved in the long cooling are so enormous that the mind can only gesture at them, never truly hold them. The age of the universe so far, from its beginning until now, is a length of time almost beyond imagining, and yet it is the merest opening moment compared to the ages of cooling that lie ahead. The era of bright stars, which seems to us the natural and permanent state of things, is a brief, early chapter. After it will come ages upon ages of slow fading, each far longer than all the time that has passed so far, as the universe eases by degrees toward its long, cold rest. It can be tempting to feel a kind of sadness at this, at the thought of all the lights eventually going out. But it is worth remembering where we stand in the story. We are here in the universe's bright morning, surrounded by stars, in the rare and warm and active age when light and heat are everywhere. The long cooling is real, but it is unimaginably distant, a faint and gentle trend rather than an approaching shadow. To live now is to live in the warmth, in the age of stars, when the cold of the far future is only the softest of distant directions, nothing that touches the warmth of a single present night. And the long cold, when it finally comes, will not be a violence done to the universe, but the universe simply coming to rest. All the great activity of stars and worlds, all the burning and colliding and shining, will slowly give way to quiet, the way a long and busy day gives way to evening and then to night. There is no catastrophe in it, only a settling. The universe will lie down, at last, into a stillness that is gentle and even and almost complete. And even then, true to everything we have learned, it will keep its one last small motion, never entirely still, all the way to the end of time. It is enough, for tonight, to rest in the warmth of the present age, in the bright, early morning of a universe that will take an unimaginable span of time to grow cold. The stars are still burning, the light is still everywhere, and the long cooling of everything is only the faintest and most distant of trends, nothing that reaches into a single present moment. We live in the age of warmth, surrounded by fire and light, and the cold of the far future is no nearer to us than the far end of time itself, which is to say, not near at all. So we come to rest where we began, with the gentle truth that cold is only the slowing of motion, the quieting of all the restless activity of matter into something calmer and stiller and more at peace. From the chill of empty space to the dying star's frozen cloud, from the floating laboratory to the long cooling of the entire cosmos, the cold is always the same thing, the same easing toward rest, and it never, anywhere, reaches the very bottom. There is always one last small motion left, and there always will be. Let us gather the whole journey together now, gently, the way you might gather a single thought before sleep. We began with the simple truth that cold is not a thing that arrives, but the absence of motion, the slowing of the endless trembling that fills all matter. Warmth is activity, cold is rest. And because slowing has a limit where speeding up does not, the question of how cold the universe can get has a shape and a bottom, a floor that everything falls toward. From there we traveled outward, down the long staircase of the cold. We found that empty space is not truly empty, but filled everywhere with the faint, leftover glow of the beginning, holding the whole sky at a little under 3 degrees above the bottom of the scale. We found the cold corners of our own neighborhood, the distant icy worlds, the craters where sunlight has never fallen, the swift cold of airless nights, each of them colder than the last, and all of them warmer, still, than the open sky. We found the one place in all of nature known to be colder than space itself, the expanding cloud around a dying star, chilled to about 1 degree above the bottom by the simplest of mechanisms, a gas flung outward so fast that it cooled below the temperature of everything around it. The coldest natural place we know is a refrigerator built by accident out of a star's slow death, and it revealed itself not as a light in the dark, but as a soft shadow cast on the oldest glow there is. We found, too, that the lowest cold of all is not in the sky but here, in quiet rooms on the earth and in a small chamber circling overhead, where patient hands have cooled faint clouds of atoms to billionths and trillionths of a degree above the bottom, colder than anything nature has ever made on its own. The coldest place in the known universe is most likely a made thing, a stillness gathered deliberately where none had ever been, drifting silently above us a few times each day. And we found that as matter nears the bottom, it does not simply freeze into a lifeless stillness, but settles into a strange and gentle harmony, currents flowing without friction, liquids creeping without resistance, separate atoms merging into a single, calm whole. Cold does not break matter down. It smooths it out, lets it fall into step with itself, releases it from the chaos of warmth into a quiet and coordinated calm. But through all of it ran a single thread, the quiet truth of the cold, which is that the bottom can never be reached. Absolute zero is a horizon, real and fixed and forever ahead, approached by endless smaller steps and never arrived at. And the reason is the gentlest one of all. Even at the very bottom, even in the coldest thing that could ever exist, a last small motion remains, an irreducible trembling that the rules of the world will not allow to be removed. The universe keeps, in everything, one final faint heartbeat of motion. There is real comfort in that, here at the close of the night. It means that perfect, total, final stillness is not something the universe contains, not anywhere, not ever. Every cold place keeps moving, faintly, always. The dying star's frozen cloud, the floating laboratory, the far future cosmos easing toward its long, even quiet. Every one of them holds that last small motion and carries it forward without end. Nothing in all of creation is ever entirely, finally still. So when we ask, one last time, how cold the universe can actually get, the answer is almost, but never all the way. It can come remarkably close to perfect stillness, closer than the mind can easily picture, and it always stops just short, by the smallest possible margin, holding back one last trembling that cannot be taken away. The cold is not a hostile thing reaching for us out of the dark. It is only what is left when motion grows quiet, and even the quietest place keeps a small motion still. Let that be the thought you carry down into sleep. You do not have to come to a perfect stop. Nothing in the universe ever does. Even the coldest, stillest place that could ever exist keeps one small motion, one faint and constant warmth of being. And so may you, as everything else grows quiet and slow and soft around you. There is no need to reach the bottom. There is only the gentle settling toward rest, the slowing, the quieting, the easing down. It is worth saying, plainly and gently, that none of this far future cold has any reach into the warmth of the present. The long cooling of the universe unfolds across spans of time so great that they have no bearing on any life, any night, any moment that we will ever know. We live in the warm early age of the cosmos, and the cold of its distant evening is no more a weight upon us than the eventual cooling of a fire is a weight upon those gathered around it while it still burns bright. The far cold is a fact about the shape of time, not a shadow over the present. There is even a strange beauty in being here so early, in the age of stars, in the warmth and the light. We are among the first to look out and understand any of this, to trace the cold from the empty sky, to the dying star, to the floating laboratory, to the far future of everything. To be alive now is to be alive in the universe's bright morning, when the warmth is everywhere and the long cooling is only the faintest of distant trends, a thing to be understood and wondered at rather than feared. The cold of the far sky is a fact to hold gently, not a fate to dread. And so the long cold ahead becomes, in the end, not a heaviness, but a kind of peace. The universe is easing, slowly and across unimaginable ages, toward a rest that is gentle and even and quiet. And even in that rest, it will never quite come to a stop. There is no harshness in the picture, no sudden ending, only the softest of long settlings, the great warmth of the early cosmos giving way, over ages beyond counting, to a calm that spreads everywhere and stays. It is the gentlest possible shape for the end of all things, and it is very far away, and tonight there is only the warmth. And perhaps that is the gentlest truth to carry down into sleep, that the universe, for all its eventual cooling, is never in any hurry and never comes to a perfect stop. It eases toward its rest across ages beyond all counting. And even at the very end it keeps one last small motion, never entirely still, never wholly silent. There is no sudden ending anywhere in the picture, no harshness, no alarm, only the slow and patient settling of everything toward a quiet that is somehow never quite complete. The universe lies down, in the end, the way you are lying down now, into a rest that keeps, always, one soft and constant trace of motion. And so the cold, which we began by mistaking for something that comes for us out of the dark, turns out to be the most patient and unhurried thing there is. It does not hunt, it does not rush, it does not arrive. It only gathers, slowly, in the quiet the warmth leaves behind, settling across worlds and clouds and the whole of the universe in its own unimaginably slow time. There is nothing in it to fear, and much in it to rest beside. For the cold is simply the universe coming, ever so gradually, to a quiet that is never quite complete. And so we leave the coldest places where we found them, far out in the dark and far down in the quiet chambers we have built, each one resting a hair above a bottom none of them will ever touch. There is always one last small motion that stays, even there. Let it stay in you too, slow and soft and unhurried. Let your breathing settle. Let the day grow distant and dim. Let the cold of the far sky be, for tonight, nothing but a kind of peace. Sleep well, and good night.